During the Enigma conference, the EFF did a small CTF with a couple of levels. Unfortunately, I was not at the conference, so the CTF was in the middle of the night for me, so I did not participate while it was running. But now I sat down and I solved the challenges a couple of hours later. I didn't solve the last level, but this will be kind of like quick speed run basically of the previous levels. I solved the levels before and now I just basically do them again. So let's create a folder for the CTF. Let's get started with the first level. So apparently this is like a message board. You can send messages to other profiles, and we have received one message from the US Department of National Security. And well, it's telling us that when you gain unauthorized access, you violate the Computer Fraud and Abuse Act and stuff like that. And we also can see our own profile here. So, and here's a little reference to the Hackers movie. So when we look at the messages and just click a little bit around of it, we see the URL and we see that the messages use the username. So one assumption, because obviously the first challenge and very easy, there might be access control confusion, and now we can try to access messages from this other user, and yes, that just works. You just have to modify the URL and you get the secret. So let me save that, and we can continue with the next one. So apparently it's like a Twitter thing. You can post some stuff. There are a couple of messages. If you try to log in, it says you cannot log in right now, it's disabled. And if you click on a tweet, you can see tweets, just looking at it a little bit. And then you see that there's a get parameter, a 1. So let's try to mess with that, and it gives us an SQL error. So we can assume that there's some kind of SQL injection. We can test this by putting in a valid SQL expression and see if it still works. And it still works. Now I made a mistake because I used the wrong syntax. I didn't mean to use union join. I tried to figure out how many parameters I need to do a union select from a different table to extract some data. Apparently one parameter is not enough. It has to be 2 values from the union select. So let's take notes of that. Here's in clear text easier. You do a union select with 2 values, and that doesn't cause an error, so you know that you need 2 values. So next thing is we want to find out what tables do exist. So we want to union select the tables from the information schema, in the tables table. And when we execute that, we get the list of all the tables, and we see that there's a messages, tweets, and users table available. Next thing, we want to figure out what kind of columns do exist in the different tables. It looks very similar. We take the column name, and to only get the column names for a certain table, we can add the where clause that we only want the table users, for example. And when we execute that, we see that the users have a UID and a username and a password, and we can also now directly union select this users table and extract the passwords. And the passwords looks hashed, but we cannot log in anyway, so it doesn't really matter to us. But yeah, we are just exploring right now and trying to figure out how we could find the flag. We can also find out all different usernames. Now let's try the messages table. So let's find the column names for that. And we find a message ID from and to the message and the message body. So body obviously is nice text. So let's use the SQL injections to retrieve all messages available on the board. And then we find here that send me the password for the next secret meeting, and the password is Marcus Yellow. So I assume that that is a flag. The issue is that the CTF is already closed, so I cannot validate my flags that is closed. So I assume that this must be the flag, but I'm not 100% sure. I have to check once there are some write-ups available. Okay, up to the next level. It says it's a reverse engineering challenge of the DNS Vault program. So we can download those files and check out the other files that are there. But most of them look just like a lot of text files. I have no idea what's in them because the challenge says it's a reverse engineering challenge. So for now, I think we don't have to deal with those, except we would get stuck and we wouldn't know how to get further. As I said, I did the challenges before, so I know that the Linux binary, I should have first do the obligatory check and see that it's a Linux binary. I start my Ubuntu VM with Vagrant, so I can actually debug or run the program. Okay, cool. So we can we have now access to our Ubuntu machine, and I copied the DNS vault binary into the shares folder. So now I can, we can check that it's a Linux binary and we can execute it, but I forgot to change the executable flag. And yeah, we get it, the password vault, and we can enter a password, but it tells us the password is incorrect. So now let's have a look at this binary in Hopper. We load the binary, and obviously first we want to check, find out where all the important stuff is happening. So we look for the strings and we find the please enter password string and follow the reference. So here in the main function happens all the magic. We can check the decompilation attempt from Hopper, and we can see that here it prints the password and then reads some data in with fgets, and then there's a for loop, and afterwards it does a mem compare on something and then prints apparently the password if it was correct. So we can a little bit start to reverse engineer this code. So this var before is just the iterator, the I in the for loop, because you can see it's like adding 1 every time and then checking if it's 14. The var 70 is related to the fget, so that is the data we input. The var 50 is used down here in the mem compare, so the var 50 is maybe it's definitely what will be compared, and the other one is apparently the secret string. So it looks, because we are moving here DL into that address, that seems like we do something with our input, and whatever is doing that is then gonna be compared to the to all these weird bytes at the beginning of main. And so that's how we know that this has to do something like with scrambling the input. And then we can also see that it only reads hex 14 bytes, so we are not looking for something longer than hex 14. And now we can follow it here, it has an iterator, gets at the offset, so takes a character and XORs the character with hex 42, and that one is then an EDX, and that XORed input value then gets written at the secret input address, and at the end it will then, those hex 14 bytes will then be compared to this to those secret bytes. So let's write a quick program, because the XOR is obviously, you can do the reverse. So our input gets XORed and then compared to those byte values. If we want to know what the clear text input is to get to those byte values, so we can just XOR the secret here with the hex 42. So I'm just preparing the Python script to do a quick XOR decryption. So we iterate over every character from this string, and we define an out variable, and then we take the value of the character, XOR it with hex 42, and then we append it to our out, and then we print that. Stuxnet, the planet. Okay, that looks cool. You see that there's some gibberish at the end, but it doesn't matter. We get the flag. The reason why it doesn't matter is, and it's why it's a bit confusing, is that you have to just pay attention that they only read hex 14 bytes and only mem compare hex 14 bytes at the end. So, you don't have to think about what happens with the rest. I think it's just to throw you off. So up to the next level, level 3. So here it says that there's an encrypted message and its own crypto, and you can do a chosen plain text attack. So if you just enter here a letter, you will get an encrypted output, but it will be every time random. If you're very careful and if you pay attention, you see that a single character always returns 4 numbers and 2 values return 8 numbers. So that might give you a little bit of a hint what could be going on there, or it's definitely something that you want to look into and think about. Why does it always have 4 numbers? What is also interesting is that they are every time random. They are not the same, and that took me a minute to think about what that could mean, because it didn't make much sense to me how you could reverse the random value, but that will all make sense in a second. So I now installed with pip the Python requests module, so I can do easy requests to that, so we can automate the analysis of this. So now I'm looking for how to do the encryption request with the Chrome developer tools, and I see it's a post request, and the post data is a string as well as key, and then you just send the value, which is the plain text. And then we can return the content of like the whole HTML page that will come back. And then we can just make a for loop with a couple of tests. So we want to see what happens when you have a couple of A's, because they should be every time the same, right? And then we can just print and check what the results are. Yeah, that doesn't help us much. We should only get back the encrypt text. So I split it up for the new lines. Then we have a list with every line, and then I just count the amounts of elements I have to go back to only print the encrypted text. And yeah, now we get back the 4 numbers. So, and as you can see, they are always different. But it's important to see that they are always 4 numbers. So what could that mean? So we can also add another character, so that we have 2 characters, 3 characters, and see how it's behaving. And we notice that it's always a multiple of 4. So we have 4, and we have 8, and we have 12. So that seems weird. So maybe it's always in blocks of 4. One idea I at some point had was just maybe looking at the values of those numbers, specifically what happens if you sum up those numbers. Like, can you learn something from the sum of this? And indeed, all A's have always the value 190. Okay, so now we basically know how to break this. The same number will always have, the same character will always have the same number. So now we can just iterate over all characters and get their sum value they will be once they are encrypted. So what I'm doing here is I create a character from hex 0 up to 255. So we start with the character with hex 1, and then we notice that it just, counts back from 255 downwards. So the whole algorithm, what it's basically doing is just it takes a value of character, for example, capital A is hex 41, and then it does 255 minus those hex 41, and that number will then be split up in a sum. So it's now super easy how we can defeat this. We basically just have to divide the message into 4 number blocks, sum up that number, and then we have to do 255 or hex FF minus that number, and the resulting number will be the character that got encrypted. And to do this, I quickly just search for a Python snippet that allows me to easily split this list in equal length parts, because I always forget how to easily do this. So, and then we just get the sum of the individual blocks. We can comment out here at the top because we don't need that for now. We have figured out the algorithm. And there's a syntax mistake. I screwed up the for loop. Okay, so now we get the individual numbers, and we also get the sum of it. And now we just define an out string that will be the flag. And so we just take 255 minus the sum of those values, and from that we get the character, and that will be our clear text. And we get this week's decrypted passphrase as "Don't bull run me, bro." Okay, we can save that now, and then on to the next challenge. So here it is about a secure channel. You want to encrypt something with a public key or private key, and basically this guy is telling you, hey, please send me your PGP key. It has to have the name, depth of national security agent, and this email attached, and he will verify that you really gave him the real key and it's not man in the middle or something by looking at a color that is generated from the key. So usually you compare fingerprints of the keys or the key itself and check if that's the correct key. But in this case, there's a color generated for the key. And you can see up there that a fingerprint is very long with a lot of different characters, so they are quite unique. While in this case, they only generate a handful of colors and compare this color, and it has to be blue. So what I'm doing now is I want to script this maybe, because I'm not sure how much of brute forcing this may end up to be. So I install GNU PG for Python, and we start by getting a GPG object which takes a path as a parameter, the home directory. Usually that would be your user's home, but in this case I'm just using the current directory as the home. Okay, let's see how we generate a key. We scroll down a little bit and we find there is first of all a generate key method, and then to use that we have to specify the parameters. In this case we also want to control the name as well as the email address assigned with the key, because not only will be the color the key will later have be verified if it's blue, but also the name and the email address will be checked. And then we can use export keys to get a ASCII representation of the key, which we then can paste into the website to see the verified color it has. Let's try to execute it. But I get an error that there's an unexpected argument GNU PG home, which is weird because that the documentation said that that would be the parameter. I'm also trying to remove it because maybe the first parameter is generally maybe the path or something, but also doesn't seem to work. So the next thing to do is I check maybe if I installed the wrong package, and I'm kind of not sure it's now Python GNU PG or if it's just GNU PG, but still doesn't change anything. Now it's the point where I should maybe check if maybe this parameters really exists. So I just import this module and use Python's help on this object to see what kind of parameters it has. And when you look closely there, you see that there is a home dir parameter. So it's not GNU PG home, but it's now home dir. So apparently the documentation that I found online is not the current version. And then we can successfully execute the program and we get the public key, which we can now take and paste into the website. And it displays the fingerprint of it and generates a color, but it's not the correct color. So now we generate a couple of more keys and we test them on the website until we finally find a key that has a blue verification code. Cool, this one is blue, so we can take that one on the original site. And this person accepts now our key and sends us a message back, which is encrypted with the public key that we just sent him. Now we just have to use our private key to decrypt it. So I didn't save the private key on purpose, but this GNU PG module will save all the keys it generated in this home directory. So at the moment, actually, all those keys that we just generated are all saved. And when we try to decrypt a message, it will look for the correct private key to be able to decrypt this message. And yeah, and that key is still in there. So we can look how to decrypt it, and we can simply then just call GPG decrypt on this message, and it will find the correct private key from all the keys that were generated before. And the flag is tiny key space is bad for business. So basically there's only one challenge left, but I haven't solved this challenge. I haven't really spent too much time on looking at it. Basically all I did was just clicking on downloading the files, but once I saw what kind of files they were, I was not motivated to solve it. But I'm quite satisfied with how quickly I got through these, and I think they was still quite fun.